Now we know more about the hierarchy, the key idea behind this. Now let's have a closer look into how do we resolve a name and how do we then get the address. So the basic idea. DNS, we learned, mapping of names to IP addresses. So the host itself knows nothing, but on the host there's a little process running called the DNS resolver. So a process responsible for resolving the requests for a name. So you have a browser, for example, and running on your host, you enter a name, and then, as we will learn in some more detail, the browser wants to set up a connection to a server, but you only have the name. So first you have to ask the resolver, please tell me what is the IP address. Because for setting up a connection, a TCP connection, for example, we need an IP address. So the host has to ask a name server. But how do we get the name server? Well, we can configure this by hand. That's one way. So we can say, okay, our name server is always 8.8.8.8, asking Google. This is always a good idea. That's a different question. So we can configure this by hand, or typically we get a list of DNS servers using DHCP, the Dynamic Host Configuration Protocol, executed in the very beginning. When you enter a network via DHCP, you get, for example, our DNS servers, a list. If you want, you can set up your own DNS system. Just set up a computer, running a DNS system, type in whatever names you like, and then the host can ask this computer and you can set up your complete independent system on top of the regular internet. So this is like having a separate phone book with a complete own organization. It's still this hierarchical organization, but you're responsible for the root and for your domains and second level and all these things. You can do this, and this has been done several times to become independent of this global system where some people say this is controlled by these 13 or these 12 independent operators. Okay, the key idea is you send a request, you get a response from the name server. We learned that this is a distributed database. We have many name servers. We'll see how this works. Each name server has a local control. We access all this using a client-server architecture. So the client sends the request to the server, server processes and sends a response. That's the idea. Okay, so how does it work? And how does this structured namespace help? First of all, before we have a closer look, we have to learn there are two types of name resolution. One is called recursive resolution. Recursive, that means you ask the name server, and the name server, if the name server uses recursive resolution, will answer with the search information on error. I can't find it. But the name server is then responsible to handle everything. That's one way of doing it. So basically, you're here with your host, you ask your resolver, the resolver goes to the name server, and then the name server does something magic, whatever, but will answer. That's recursive. The name server is responsible for handling whatever. The alternative is an iterative resolution. So the host again asks the name server, and the name server may come back with the correct resolution or come back with an address of the next name server. And then, if this is the case, your resolver has to contact the next one. And maybe this one is recursive, doing all this and answering directly. So recursive and iterative resolution. What does it mean? Once more, and then I will give you an example for this. Basically, recursive is nice because the client offloads the task. So our host simply says, you name server, please handle the problem. And maybe this name server has to contact another one. This doesn't give back the answer, then you contact yet another one. And this still does not give the correct answer, then you have to connect yet another one. And then this finally gives the answer, and the answer is returned. That's a recursive query, and the host doesn't care. The job is on the name server here. That's offloading. For iterative queries, well, that's simpler for the name server, because it could only return the address of the next one. So the host asks the name server, and either the name server has directly the answer, or at least it knows whom to contact next. And then the host, the resolver, has to contact the next one, etc. So the load now is on the resolver of the host if you perform this iterative query, but you offloaded a lot from the name server. And we can mix the concepts. So an example. Let's assume you asked to connect to this giri whatever in Australia. Then your host will ask the resolver. Now assuming the resolver doesn't know anything. So the resolver goes to the name server and asks, name server, I've got a request. The name server itself has no idea, has never ever heard something from Australia. So down under, I don't know. That means the name server has to contact a root name server. So I have no idea. I know at least, well, the root. Yes, great. I know the root. But tell me the address of this specific computer. Root name servers don't know all the computers. So, but at least they know who is responsible for the top level domain for Australia. This is an iterative resolution because the root name servers, and by the way, root name servers never operate recursive. Root name server answer the iterative resolution. They give you a pointer to the next one. Recursive would put too much load on the roots. So they answer with, I know at least who's responsible for Australia. I have no idea what gov is there and whatever Gimbpa and Giri, I don't know. So then the next step is I have to ask the name server for Australia. And this at least gives you then a reference to gov.au, so some governmental server. You see, from the resolver's point of view, this is recursive because the name server handles this somehow. So we have this combination. And then you can imagine how it continues. Well, at least the AU name server gives us the responsible for government, and then this gives us responsible for GB, RMPA, whatever at the government. And then this name server finally has then the address. So here, the last step in this example, we get the real address. So all these servers on the right-hand side, they operated with iterative resolution. You see, they never continued for you with the search. They only gave a reference to the next one. The name server you contact operated recursive because, well, it took care of, okay, asking this one, asking next one, etc. And then finally you get your response. That's the idea. So it could have been done also another way. Imagine we could, for example, instead of giving you the reference here, this name server could also have asked the next one. That would be then recursive, because you asked the next one on behalf of your first request. This could have also, well, operated recursively or iteratively, so different combinations are possible. And then, if we have the situation like this answer here would have given directly here. So our name server would save an additional step. Or we could even go down to the next and then go up, etc., and send back the address already here. So you see, different combinations are possible. This also depends on how many levels you have, etc. So if we assume we have something like www.name.com, we need only 3 queries. If we don't know anything, one for who's responsible for .com. Next one, then we ask the .com database who is responsible for name, and then we get back the address of the web. So that's possible from anywhere in the world, 3 queries, and to speed up the system we have these distributed root servers, etc. It's important how you see this hierarchy reflected in the delegation of the data stored. The root doesn't store the details of anything inside the DE space. Why? The DE register doesn't store the details of the names inside, for example, FU Berlin. DE only knows FU Berlin. That's the idea. A big single database would simply be overloaded. And central servers may be too far away, so we have huge access times, etc. So local control is also better from a political point of view. Just think the idea of asking central authorities if you want to change something. So, and we will see examples where we have exactly this problem. So load balancing, distributing, this increases pretty much scalability. So you only store tiny parts of the database, so smaller databases, but distributed. So that's the idea. And we make sure that we have at least one point where we store the information. So one well-known location. We have the primary, masters, and they know what's going on in the zone. So that's the idea. So we spread the system. We know in the worst case whom to ask, but we at the same time try overloading the roots, etc. So as you see, it's quite simple. These 3 queries, we find the IP address, 129 dot whatever it is. Can we do the other way around? And the other way around is called a reverse lookup. So we know how to perform a DNS lookup. That's the classical one. And we build a database indexed by names. That's our tree, and inside database we store parts of the tree. So mapping of a name to an address is simple. We saw this. 3 requests to databases and we got the address. But to do it the other way around is a bit more difficult. So do you want to search the whole namespace? Because we have addresses, and the address, the number, has nothing to do with the name. So it's not the case that a certain IP address automatically belongs to a certain zone. No. So mapping of an address to a name is more difficult. But so this reverse lookup, But we don't want to build a complete new system, so to speak, a second database that's now somehow organized in a complete different way. No, can't we reuse the DNS system for also this reverse lookup? And that is one of the core ideas. We have a special area in our database, in our normal DNS database, with addresses as index. And there's a special domain name for this area. It's not that well known to many people. So we have this internet address.arpa. And there we have, and this is now for IP version 4, there we have this address ARPA domain has 256 subdomains, because each part of this 4-byte IP4 version 4 address is a byte, so max 256. 256 subdomains, which again has 256 subdomains. I will show you this in a second. And on the last level, then the resource record stored is then assigned with the IP address. And we read the whole address backwards. Oh, how does this work? So, in the end, and then with the help of the next slide, you will understand that the computer with the IP address shown here, this 15.16.109, whatever, that's the IP address, is stored here in this subdomain. Okay, so basically then the names are now, well, the IP address in reverse, plus we add this internet address.arpa. And for IP version 6, we have the IP6.arpa domain. So how does it work? So we have this tree, and this is how it starts. And maybe you remember we have the .com and whatever, mil, de, blah, 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 all the others. And we also have this ARPA. And ARPA, we have this internet address. And then the next level is exactly this subtree here, and then the next subtree, and the next subtree. And now level 4, because we have these 4-byte addresses, and there we attach the host name, for example, vinny.corp.hp.com. So we now know the computer here, the name that belongs to an address. So if we see a certain address, with the help of this database, we simply go through the tree, taking each byte out of the address, and then we will find the name. So if we have an IP address, we take the IP address and simply go down the tree. Why do we need this? Who on this planet wants to map an address to a name? Well, maybe you received, could be the case, faked emails, spam, phishing stuff, also spoofing. So does this IP address really belong to a certain, or coming from a certain server? Does this really belong to this computer? Or is it just claiming? So, if you want to know this, and this is very useful against spoofing, you can check if you receive a data packet that claims to come from a certain computer. With the help of this reverse lookup, you can check if this is really true. There are some conditions like, well, the database has to be protected and no one, did something wrong with the database, etc. I will come back to this, to the security issues later. But so you have to understand that we use the idea of this tree, of this huge database, also for a reverse lookup. If we store and all the nodes, and you see these are quite many, the names of these computers. So there are some problems with that. I will come back to it. Okay, some questions. So let's go back. We saw there are recursive and iterative resolutions possible? What's the difference? Why do we do recursive? Why do we do iterative? Why do root servers not really like recursive resolution? And how does this together contribute to scalability? We don't do this just for fun. So this all contributes to the core issue, scalability. Then we had a quick look into reverse lookup. You will find a lot of literature about this. Why do we need this? When do we need it? And why does it quite often not work? This is something you might not be able to answer. You need some more information for this, coming up in the next slides. So because if you try this quite often, you do a lookup for this address, quite often you will not get back the name of the computer as an answer because something is missing. Well, you can try. Just try. I will show you the tools and do a lookup using this reverse lookup idea, and you will find out.